Assalamualaikum and welcome to the video. In this video, we are going to discuss Chapter 5, Work, Energy and Power. In this section, we are going to discuss work. So if you look at the slide, I have two equations here. The first equation is impulse momentum theorem. And then the second equation is the equation for work energy theorem. At first glance, you will see that there is some similarities between the two equations. So in impulse momentum theorem, you have the force times with how long the force is applied, which is the time, and then the product of force times with the time is going to be equals to the change in the momentum of the object. And then in work energy theorem, so delta K here, the K stands for the kinetic energy. So kinetic energy is a type of energy. So work energy theorem says that the force that is applied to an object times with how far the object has been moved or displaced. So the dot product of force with displacement is going to be equals to the change in the kinetic energy of the object. So in impulse momentum, you have force and change in momentum. And in work, you have force and change in the kinetic energy. Alright, let's look at one example. Let's say now you have an aircraft with a thrust force of 500 kilonewton. And the mass of the aircraft is 22,000 kilogram. So we are going to ignore the air resistance. So let's assume that the only force that is acting on the aircraft is the thrust force that coming from the engine of the aircraft. So you have the thrust force of 500 kilonewton. So and then the value of the thrust force is constant. So now if the aircraft is accelerate forward, so it moves to here. Okay. Let's say the time taken for the aircraft to move from the initial point, the original point, to the new position. It takes the aircraft, let's say, around 4.4 seconds. And then the distance moved by the aircraft is 440 meters. Alright, so that is the distance moved, and this is the time for the aircraft to get to 150 meters per second from 50 meters per second. So in this situation, we are assuming that the force of the engine is constant. So at the velocity of 50 meters per second, if you calculate the initial momentum of the aircraft, so you are going to be multiplying the mass of the aircraft times the initial velocity. So 22,000 times with 50, you are going to get 1.1 times 10 to the power of 6 kilogram meter per second. And then the momentum of the aircraft at the velocity of 150 meters per second is the mass times the velocity. So 22,000 times with 150, you are going to get 3.3 times 10 to the power of 6 kilogram meter per second. Alright, so that is the momentum. Okay, then if we calculate the kinetic energy of the aircraft, so the kinetic energy of the aircraft initially, so the equation is half mu square. So 1 over 2 times 22,000 times with 50 square, you are going to get 27.5 times 10 to the power of 6 joules. And then the kinetic energy of the aircraft at the velocity of 150. So kinetic energy of the aircraft is 1 over 2 times 22,000 times with 150 square. You are going to get 247 0.5 times 10 to the power of 6 joules. Alright, so I'm going to change the color. So if you calculate the change in the momentum of the aircraft, okay, 3.3 minus 1.1 is going to give you 2.2 times 10 to the power of 6 kilogram meter per second. And then if you calculate the change in the kinetic energy of the aircraft, 247.5 minus with 27.5, you get 220 times 10 to the power of 6 joules. So now I think I'm going to clear out the calculation for the momentum and kinetic energy. So we have calculated the change in the momentum of the aircraft and the change in the kinetic energy. So for the examples here, the force 500 kilonewton is applied on the aircraft for 4.4 seconds. So that is how long the force is applied on the aircraft. So if you multiply the force with how long you apply the force, alright, the force is 500 kilonewton times 10 to the power of 3 times with how long the force is applied, 4.4 seconds, you are going to get 2.2 times 10 to the power of 6 Newton second. So if you look at the value is the same as the change in the momentum of the object. The value that you calculate here is the value of the impulse of the aircraft. Alright, so this verify the impulse momentum theorem. So impulse is the amount of force, the net force that we apply to an object, times with how long we apply the force, is going to be equals to the change in the momentum of the object. So that is what we have done here. Alright, so now the force displaced the aircraft by a displacement of 440 meter. So if you multiply the force times with how far the force has moved the object, alright, so the force is 500 kilonewton times 10 to the power of 3 times with the displacement 440 meter, you are going to get 220 times 10 to the power of 6 joules. Alright, so if you look at the value of force times with the how far the object has moved is the same as the change in the kinetic energy. So the amount of work that is done on the aircraft is 220 times 10 to the power of 6 joules. So what the value that you calculate here is actually the work done by the force. Alright, that is the definition of the work done. So this verify the equation work energy theorem, where work can be written as the force dot with the displacement, alright, is equals to the change in the kinetic energy of the object. Okay, now we are looking at the graph. So if you look at the graph, because the force is a constant, that's why we have a flat line here. So if you look at on the y-axis, we have the force in kilonewton, and then on the x-axis is the time, how long the force is applied. So the red line is the red line here is the magnitude of the force, and then the time is 4.4 seconds. From the impulse momentum theorem, so J is equals to F delta T is going to equals to delta P. So F delta T here is telling us that the area under the graph of F against T is going to give you the impulse or the change in the momentum of the object. So if we calculate the area of the graph, so 500, but remember the axis has a prefix k there, so k stands for 10 to the power of 3. So times with the time 4.4, you are going to get 2.2 times 10 to the power of 6 Newton second. Alright, so that is the value of the impulse. Alright, so now on the right we have the force, but now on the x-axis we have the displacement, how far the object has been displaced by the force. So if we calculate the area under the graph, you are going to get the amount of work done by the force. Alright, so we have the equation. The work done is the dot product between force and displacement. I'm going to explain this later, alright, which is equals to the change in the kinetic energy. Alright, so by calculating the area under the graph Fs, so if you look at the equation here, F times S will give you the area here. Alright, so the area is going to give you the work done by the force. So we have a force of 500 kilonewton times with the displacement 440, you are going to get 220 times 10 to the power of 6 joules, which is also equals to the change in the kinetic energy. Alright, so this is also equals to the change in the kinetic energy, and impulse here is equals to the change in the momentum. Alright, so in the next slide we are going to look at how we are going to use the equation F dot S. So if you look at the equation of work done, the equation of work done is equals to the dot product. So the dot is stand for a multiplication. Alright, so you multiply the vector force with the displacement vector. So the way you calculate the dot product is by multiplying the magnitude of the force times with the magnitude of the displacement and then cos theta. Theta is the angle between the vector force and the vector displacement. In this slide, I'm going to show you how we can determine the angle theta. So if you look at the diagram here, we have a block and we have an external force acting on the block. The magnitude of the external force is 10 Newton. So when the block is pulled by the force 10 Newton, the block moves forward and then has a displacement of 2 meter. So the magnitude of the displacement is 2 meter. So the forces that is acting on the block, the weight of the block, and then the normal to the block, and also the friction by the floor. So if we draw the free body diagram, so I've prepared for you the Cartesian and the dot there for us to draw the free body diagram. This arrow will represent the external force. This arrow will represent the weight. This one will represent the friction. And this one will represent the normal. So if we put in all the angles, so the angle here is 45 degree. Alright, so now how do we determine the angle theta? But before that, I need to draw the displacement vector. So the displacement vector is because the block is moving in the positive x direction, so the displacement vector is also going to point to the positive x direction. So I'm going to draw the displacement vector in red. So that is our displacement vector S. Alright, this is our external force. So this is the external force, this is the normal, this is the weight, and this is the friction. So by looking at the diagram, the angle between the external force and the displacement, alright, this is the vector external force, so the angle between them, so angle between the external force and displacement is 45 degree. Okay, and then the angle between normal and the displacement is 90 degree. Okay, this angle here, so that angle is 90 degree. And then the angle between the weight and the displacement is also 90 degrees. So this angle here, so this angle is 90 degrees, and the angle between the friction and the displacement, because they are pointing in opposite direction, so the angle between them is 180 degrees. So I'm going to use the green color. So from here to here is 180 degrees. So the angle of the vector friction to the displacement is 180 degrees. So this is the first step to calculate the work done on the object, the net work done on the object. Okay. In the next slide, I'm going to show you the method that I've used to systematically solve for the net work done on an object. Let's go there. Okay, so to truly understand how we can use the equation to calculate the work done by the force and also the net work done on the object, so I'm going to give you two examples. I'm going to do two examples. The first one where the object moving with a constant velocity, and the other one where we have acceleration in the object. If you read the questions, it says you have a 2 kilogram block displaced by 2 meters from its original position and moving at a constant velocity. So the terms constant velocity implies that the resultant force of the resultant force in x and the resultant force in the y is 0. So we are going to write Fr of x equals to 0 and Fr of y equals to 0. Sometimes we use the sum of force in x equals to 0. So these two means the same thing. Alright, so instead of the sum of Fx, I'm going to use Frx. Okay, so we have the initial condition there, and then it is given to us that the kinetic friction between the floor and the block is 7.07 Newton. Okay, the reason why they give you the kinetic friction is because the object is already moving. So we have drawn the free body diagram. So from the free body diagram, we can resolve or fill up the tables with the component of the force. So if we look at the external force, the angle between the external force to the x-axis is 45 degrees. So the x component of the force is positive 10 cos 45, and the y component is 10 sin 45. Okay, I hope you know how and where do I get these two values from. Alright, and then you can do it yourself to verify that you can get the 10 cos 45 and 10 sin 45. And then for the weight, so the weight can be calculated using the equation. Weight is equals to m times g. So the mass is 2 kilogram. The gravitational acceleration is 9.81. So weight is 19.62 Newton. But because the weight is pointing in the negative y direction, so the force is going to be negative, and weight is one dimensional. So the x component is 0. Weight only has y component. So we have negative 19.62 here. Normal is also a one-dimensional vector only in the y direction. So x component 0, and we do not know what is the value of n, so we're just going to put n. So friction is opposing the force, so friction is going to be negative 7.07. Alright, and friction is also one-dimensional, so the y component of friction is 0. So if you add up 10 cos 45, which is equals to 7.07, alright, plus with 0, plus with 0, plus with negative 7.07, you will get 0 there. Alright, so it is verified that when you add all the forces in the x component, the resultant force in the x component is 0. So okay, now we can calculate the n from the y component. Alright, so if we add 10 sine 45, so 10 sine 45 is 7.07. So plus with negative 19.62, so minus 19.62, and then plus with n plus 0 equals to 0. So meaning that n is equals to 12.45 Newton. Alright, so we already get the value for the normal force. Okay, this is very important when we want to calculate the work done. Alright, so going to the next slide. So this is all the value that we have established before. So the x component of the force is 7.07, the y component is 7.07. So this one is 10 cos 45, this one is 10 sine 45. So this is everything that we have established from the previous slide. So if you look at the table here, I have added another 2 columns into the tables. I've added the column for the magnitude of the force, and I've added a column to calculate the work done. The way I calculate the magnitude of the force is by using the Pythagoras theorem. So magnitude of force is going to be equals to Fx square, the x component of the force square, plus the y component of the force square, and then square root. So we have 7.07 square plus 7.07 square. You are going to get back the 10 Newton. So for the weight, I'm going to highlight that. So you are going to get back 10 Newton. Alright, so for the weight, so the x component is 0, so 0 square, plus with negative 19.62 square, you are going to get back 19.62. And if you can see, the value is always positive. So calculation for the magnitude of n, so you are going to square the 0 square, plus with 12.55 square, and then you are going to square root, you are going to get back 12.55. Alright, so I'm going to erase that. Okay, so that's how we calculate the magnitude of the force there. So we have that, and then we have negative 7.07 square, plus with 0 square, and then square root all, you're going to get 7.07. So in the last row, so we have that the frx is 0, fry is 0. So if you square the 0 plus with fry square, so 0 square plus 0 square, and then you square root, to get the value of fr, you are going to get 0. Okay, so that is how you calculate the magnitude of the force, alright, using the Pythagoras theorem. Okay, I hope you can see that. So fr is 0, so I'm going to erase this part here. Okay, so we're going to substitute with 0, and then the sum of the forces in the y is 0, so 0 square plus 0 square, and then the fr is also 0. Okay, so to calculate the work, the equation to calculate the work is magnitude of the force times with the magnitude of the displacement, and then cos the angle between the force and displacement. We have determined the angles previously, okay, a few slides back. Okay, the magnitude of the force is 10 times with the displacement, which is 2, the magnitude of the displacement, and then cos the angle between the external force and the displacement is 45 degree. And then we have 19.62 is the magnitude of the weight, time with 2, and then cos the angle between them is 90 degree. And then we have the normal 12.55 times 2, also cos 90. And then the last one, 7.07 times 2, cos of 180 degree. So this will give you the work done by the force. Alright, so 10 times 2 cos 45, you are going to get 14.14. So you have here 14.14. Here cos of 90 is 0. So the whole thing is going to be 0 and 0, and this one. So cos of 180 is equals to negative 1. So 7.07 times 2 is 14.14 times with negative 1. You are going to get negative 14.14. So to calculate the net work done, the total work done on the object, so 14.14 plus 0 plus 0 plus with negative 14.14, you are going to end up with 0 joules. Alright, so that is how you calculate the net work done or total work done on the object. So you calculate the individual work done by the forces, and then you add them up, you will get the net work done. Another way you can use to calculate the net work done is by using the same equation up here. So work net is equals to F net dot S. Alright, so here we have the F net. The F net is the FR. So FR is 0. So times with S cos theta. So anything times with 0, you are going to get 0. So we get the same answer. So there is two ways you can calculate net work done. Alright, so now we are going to move on to the second examples with acceleration. Okay, in this example it says that we still have the same block displaced by the same displacement 2 meter, but now the block has an acceleration with a magnitude of 1.77 meter per second. So if you look at from the diagram, the acceleration is in the x-axis. So if you can still remember from chapter 4, we are going to take the direction of the acceleration as the positive direction. So if we go to the tables, we can write that the force resultant in x is equals to mass times acceleration, and this acceleration is in x. So it is the same as writing sum of force equals to max. Okay, they are the same thing. The block is initially at rest, so given that the kinetic friction is 7.07. Okay, I'm going to quickly calculate the normal force. So because we do not have any acceleration in the y-axis, so Fry is going to equals to 0. So just I'm not going to draw the free body diagram again. So I think you can work it out yourself. So if we resolve the vector force here, so the x component is 15 cos 45, the y component is positive 15 sine 45. The weight is one dimensional, y, so n is also one dimensional in the y. So we have negative 19.62. we have calculated this value before, so we do not have the value of n. So the friction is negative 7.07, also one dimensional but only in x. So from the y component we can calculate the value of n. So we have 15 sine 45. So 15 sine 45 plus with negative 19.62, so minus 19.62 plus with n equals to 0. So if you calculate the value of n, you are going to get 9.01 Newton. Okay, now the value of n has changed because if you look at the external force, in the previous question the external force is only 10 Newton. Now the external force has changed to 15 Newton. So in this slide I've put in all the value in the tables. So I've added another two column, the column for the magnitude of the force and column for the work. Alright, so in the previous slide we have resolved the force, okay, into x and y component. So the x component is 10.61, y component is also the same. So the magnitude of the force is 10.61 square plus with 10.61 square you are going to get back 15. Okay, I hope you understand how do I get this value from. The second one is 0 square plus with negative 16.62 square and then square root. So you are going to get this value. Same goes for the magnitude of the normal and also the magnitude for the friction. Okay, so except for in these examples the resultant force in the x direction is not 0. So 10.61 plus with negative 7.07 you are going to get 3.54 Newton. So that is the sum of the force in x. So if you use the equation here to calculate the acceleration, so Fr of x equals to m times with a. So Fr of x is 3.54 equals to 2 times acceleration. So acceleration is equals to 1.77 ms negative 2, which is the value that is given to us in the questions. Alright, so we get that part right. So in the y component, because we do not have any acceleration in the y-axis, so the resultant force in the y-axis is 0. So the resultant, the y component of the resultant force is 0. So the Fr is just 3.54 square plus with 0 square. So you are going to end up with the same value, 3.54 Newton. So that is our net force. So because now we have the net force, we can draw the net force to get the direction of the resultant force. So if we draw the direction of the resultant force, because I'm just going to quickly draw it here. So we draw the Cartesian first, so that is y-axis, and this is the x-axis. Okay, so 3.54 is positive, and if you remember from the previous slide, we take this direction as positive direction. So meaning that the resultant force, because it only has one component, so our resultant force is one dimensional. I think I'm going to use a green color. So our resultant force is this one. So the green one is the resultant force. So this is our Fr, and the magnitude of Fr, because it is one dimensional vector, the length or the magnitude of the Fr is 3.54 Newton. Alright, so I'm just going to quickly draw the displacement vector. So displacement vector, so the object is moving to the positive x direction. So from the drawing, we know that the angle between the F resultant and displacement is 0. Okay, this will become important in just a bit. Alright, now we are going to calculate the work done by the force. Okay, we have the first force, which is the external force. So the work done by external force is 15 times with the displacement 2 and then cos 45. So 15 times 2 cos 45 is 21.21. Okay, joule. And then we have 19.62 times 2 cos of 90. We know that this is going to end up as 0. And also same for this one, cos of 90, because they are perpendicular to the displacement, so they are not going to contribute to the energy of the object. So this is also going to equals to 0. And then finally we have 7.07 times 2 cos 180. So we get negative 14.14. So the net work done is 21.21 minus 14.14. So we get the net work done as 7.07 joules. I have told you before that there is another way we could use to calculate the net work done. So I'm going to clear out the drawing at the bottom here. Another way to calculate the net work done is W net, work net, is equals to F net dot S, alright, equals to magnitude of the F net times the magnitude of S cos of theta. So the magnitude of F net is 3.54. So 3.54 times the magnitude of displacement is 2, and then cos of 0 because they are parallel. So we are going to get 7.08. Just slightly different. So if you look at the value here, so the value that we calculate up here and the value that we get from the second method, they give you the same value. So there is two ways you can calculate the net work done. Either you want to do it individually, calculating the work done by the force, or you can just calculate the resultant force and then use the resultant force or the net force to find the net work done. Alright, I think that is it for this section. We are going to get into the second section. So welcome to the second subtopic. In this subtopic, we are going to be dealing with mechanical energy. Alright, the first one is the kinetic energy. Kinetic energy of a moving object. So any moving object will have a kinetic energy. The equation is half mv square, mass times the velocity square. And then the second one is the potential energy. We have two types of potential energy. The first one is the elastic potential energy. This is where you have a spring. So let's say you have a spring. So this is your spring, and then you elongate the spring. So you extend the spring. Now you have an elongation of delta x. Delta x is how much the spring is being elongated. You can also compress the spring. So this is the original length. So now the length is shortened. So this is going to be the delta x or the x. Alright, so x here can be elongation. So it can be elongation or compression. So basically x is the change in the length of the spring. So if you multiply half k with the x square, you will get the elastic potential energy stored in the spring. And then we have gravitational potential energy. So gravitational potential energy is U equals to mg times height. Alright, so this is the height. Alright, so the height is always measured from ground. So you need to pay attention to this part here. So the height of the object is measured from the ground. So now we are going to discuss another conservation law, which is the conservation of energy. So to illustrate the idea of conservation of energy, we are going to drop a ball from rest. So the initial velocity of the ball is 0 meter per second. So the height of the object is, let's say, 100 meter measured from the ground. So this is our ground. So from ground to the ball is 100 meter. And vertical displacement of the ball currently is 0 meter per second, because we drop the ball from this height. So this height is going to be our origin. So the SY is 0. So if we calculate the potential energy, capital U, let's say the mass of the object is 1 kilogram times the gravitational acceleration magnitude. The magnitude of the gravitational acceleration 9.81 times with the height. Alright, so we get 981 joules. And then if we calculate the kinetic energy, half m, because the velocity is an initial velocity, so we are going to multiply with u instead of v. So u stands for initial velocity, because it is dropped from rest, so the initial velocity is 0 joule. So this is the initial or the origin of the object, and then the object fall down. So now the height, let's say the current height is 70 meter. So 70 meter is measured from the ground to the ball. So that is the height, 70 meter. So because the height is 70 meter, so the displacement, the vertical displacement of the ball is negative 30 meter. Alright, negative because of the ball is going downwards. So the displacement Sy is from the origin. Sy is measured from the origin to the ball here. So this displacement is negative 30 meter. So if we calculate the magnitude of the gravitational potential energy, so 1 times with 9.81 times with the height, 70, we get 686.7 joules. And then to calculate the kinetic energy, we need the velocity. So we are going to use the equation Vy square, Uy square minus 2gs. So Uy is 0, so minus 2 times 9.81. So now we are going to substitute the value of Sy, negative 30. Alright, so we are going to get 588.6. So 588.6. Alright, so this is the value of Vy square. So Vy is equals to plus minus 24.26 meter per second. But because the ball is falling downwards, is falling down, so we are going to take the negative value. So the velocity of the ball is negative 24.26 meter per second. Alright, so the kinetic energy of the ball, I think I'm going to use a different color, blue. Alright, so kinetic of the ball is half mv square. So if you substitute the m and the v, 24.26, you are going to get 294.3 joules. Okay, that is at the height of 70 meter. And then the ball continue to fall. Now let's say the height is 30 meter above the ground. So 30 meter is measured from the ground, and the vertical displacement is measured from the origin. So it's going to be negative 70 meter. So the potential energy is mgh. So m is 1 times 9.81 times the height 30. So you get 294.3 joules. So and then if you calculate the kinetic energy, so kinetic energy is K. I'm using the blue color. So K, we need to calculate the Vy first. So Vy equals to Uy square minus 2gs. We just substitute the value and you get the value of Vy equals to negative 37. I'm not going to show you how I get this. I hope you can do it yourself. Negative 37.06 meter per second. And if we substitute the value into the equation half mv square, we are going to get a value of 6. Sorry, I'm going to change the color to blue. So 686.7 joules. Okay. So that is at the height of 30 meter. Let's say now the ball is already on the ground. So now the ball is on the ground here. So the current height is 0. So the height is 0 and Sy is negative 100 meter. So if you calculate the value of the potential energy mgh, you will get, because the height is 0, you get 0 joules. But when you calculate the kinetic energy, alright, so we need to calculate the velocity first. So Vy square equals to Uy square minus 2gs. So the s is negative 100. So Vy, you are going to get negative 44.29 ms negative 1. So the kinetic energy of the ball on the ground is equals to 981 joules. Okay. So I'm going to highlight each section. So this is the first section. I'm going to highlight with a yellow highlighter. So just to differentiate them. So the second section here. So this is the purple one. So this is at the height of 70 meter. And then I'm going to use the blue. So this is the height of 30 meter. So this is the potential energy and this is the kinetic energy. So and then using green. So green is for the height of 0 meter. So the potential energy goes to 0. The kinetic energy is 9.81. Alright, so if you calculate, so let me just highlight the height here. Okay, so if you calculate at each point during the fall, you will get the total kinetic energy of the ball. So 9.81 plus with 0, you get 981 joules. Okay, so I'm going to clear out the calculation that we do for the velocity. So if we add the potential energy plus the kinetic energy at the height of 70 meter, height equals to 70 meter. So when you add the U plus K, 686.7 joules, the potential energy, plus with the kinetic energy 294.3, you are going to get 981 joules. So when you add U plus K at the height of 30 meter, alright, you have the potential energy 294.3 plus the kinetic energy 686.7. Okay, you are going to get 981 joules. The same for when you add U plus K at the ground. So you have potential energy 0, kinetic energy 9.81. So you will end up with 981 joules. So if you look at the value does not change. The value stays the same. Alright, the sum of the energy is the same. This demonstrates conservation of energy. So this is what it means here. Total energy of the closed system is always conserved. Whenever or wherever you calculate the total energy of the system at any point, alright, you are going to end up with the same value, 981 joules, 981 joules, 981 joules, except for the value of U and K is going to be different, but the sum of U and K will always stays the same. Hello and welcome to the third section of the video. In this video, we are going to look at the idea of power. So power can be defined as the rate of work done or the rate of energy transfer. Okay, let's look at the previous example that we have done in the video. So in this video, we have an aircraft and then a thrust force that is pushing the aircraft forwards. So in this example, we ignore the air resistance. So the only force that is acting on the aircraft is the thrust force. The thrust force from the engine of the aircraft increased the velocity of the aircraft from 50 meter per second to 150 meter per second. So the change in the kinetic energy due to the thrust force is 220 times 10 to the power of 6 joules. Alright, so how do you calculate the power delivered by the engine of the aircraft? So the power is given by equation power is equals to the rate of work done, W over T, or change in the kinetic energy over time. There is two ways you can calculate power. So we already have the change in the kinetic energy, 220 times 10 to the power of 6 joules, divided by how fast that change happened. So it took 4.4 seconds. So divide by 4.4, you are going to get 50 times 10 to the power of 6 joules per second, or we normally write it as 50 times 10 to the power of 6 watt. So watt is the unit for power. So power is basically how much energy is gained by the aircraft due to the force per second in 1 second. So from here we know that the force increase the energy of the aircraft by 50 times 10 to the power of 6 joules every second. That is how much energy is being delivered to the aircraft. So the power due to the thrust force is 50 times 10 to the power of 6 watt. So that is how you calculate the power. I hope this gives you some ideas on what power really is. Hello and welcome. In this slide I'm going to discuss the average power and the instantaneous power. So let's say the question asks you to find the average power delivered to the block to move the block from point A to point D, and let's say it takes 4 seconds to get to point D. So the average power delivered to the block is equals to work done over time, or just equals to the change in the kinetic energy of the block divided by time. So if we want to use the first equation here, which is the work done over time, you need to calculate the net work done on the block. So work done, the first work done that we have is from the external force. So 10 times the displacement, 20 cos of 0, and then the other one is from the friction, 10 times 20 cos of 180 degree, and this one will give us 200 joules, and this one is going to give us negative 200 joules. So I'm not going to calculate the work done by the normal and also the work done by the weight, because they are perpendicular to the distance, to the displacement. So cos of 90 is just going to give us 0. So the average power delivered to the block is the total work done over time, which is equals to 0 over 4, so equals to 0 watt. So there is no average power delivered to the block. So this is how you use the first equation. So if you want to use the second equation here, delta K over delta T, it should give you the same answer. So because the object is moving at a constant velocity, so the change in the kinetic energy, which is half mv final minus half mu final square, is going to be equals to 0. So the average power delivered to the block is 0 divided by 4. You will get the same answer, 0 watt. Alright. So now I'm going to clear out the section below. So what if the question asks you to find power instantaneous? So we are still going to use the same equation, work over time, but now we are going to use the force times displacement over time. So Fs over T is force times with velocity. Let's say the question asks you to find the power instantaneous at T equals to 4 seconds. So at point D. So and the instantaneous power is for the external force. So then you are going to use the external force times the velocity. So external force is 10 times velocity at 4 seconds, because the object is moving with a constant velocity. So the velocity of the object at 4 seconds is also 2 meters per second. So the instantaneous power delivered by the external force is 20 watt. Alright. Okay, now we are going to move on to the second examples, where we have object with an acceleration of 2.5 meters per second square. If the initial velocity of the object is 0, so after 4 seconds, the velocity of the object is going to be 10 meter per second, because the acceleration of the object is 2.5 meter per second times with 4 seconds, we have 10 meter per second. Alright, so let's say the question asks you to find P average delivered to the block. So we are going to use the equation work over time or change in the kinetic energy over time. I'm going to show you how to use the first equation here. So we have two forces there. We are going to do the same, except for now the magnitude of the external force is bigger. So 15 times 20 cos of 0, you get 300 joules, and then work done by the friction is 10 times 20 cos 180, you get negative 200 joules. And I'm not going to calculate the work done by normal and weight. As I've shown before, their work is 0. So the average power delivered to the block is going to be the net work done, which is 300 plus with negative 200. So you have 100 joules, and this change happened in 4 seconds. So this is the average power delivered to the block to move the block from point A to point D with an acceleration of 2.5 meter second negative 2. So we get 25 watt. Now we are going to use the second equation, delta K over T, to find the average power delivered to the block. The mass of the block is 2 kilogram. Alright, so the change in the kinetic energy is half mv square minus half mu square. So equals to half times 2. The final velocity is 10 square minus half times 2 times 0 square. So you will end up with 100 joules. So that is the amount of change in the kinetic energy of the block to move it from point A to point D. So P average power, the average delivered to the block, is 100 joules divided by 4 seconds. So you get the same answer, 25 watt. I think that is it for average power. Now I'm going to clear out the section here to explain about instantaneous power. Okay, now we want to calculate the instantaneous power delivered to the block. So at point B, the velocity of the block is, let's say we write it as VB. So VB is 2.5 meter per second. So at VC, the velocity of the block is 7.5 meter per second, and velocity of the block at point D is 10 meter per second. So if we want to calculate the P instantaneous power delivered to the block, so we are going to multiply the force to the block times the velocity. So the force is going to be the net force that is applied to the block. So we only have a net force in the x direction. So 15 minus 10, you have 5. So let's say you want to find the instantaneous power at t equals to 1 second. So t equals to 1 second. So you're going to substitute the velocity of the block at 1 second equals to 2.5. So you're gonna get 12.5 watt. Alright, so this is the instantaneous power at t equals to 1. So let's say you want to find the instantaneous power at t equals to 4. So we are going to multiply the net force, which is 5, times with the velocity at t equals to 4 is 10. So the instantaneous power delivered at t equals to 4 seconds is 50 watt. Alright, so I hope you can now differentiate between average power and instantaneous power. That is it for this video. Thank you very much. If you have any questions, we are going to discuss them during our Google Meet session. So thank you and bye bye.